with an example, and this example is the limit of x minus 2 divided by x cubed minus 8 as x going to 2. Okay, so we want to find this limit. We are taking the limit of a rational function, right? And notice that if I plug in x equals to 2 in the fraction, I am getting what? 0 divided by 0, right? So it doesn't tell us what the limit is. Sometimes students in the exam say, oh, it's 0 over 0, the limit is undefined, okay? Be careful. 0 over 0 doesn't tell you what the limit is. It only tells you that the fraction is undefined at 2, okay? And if a function is undefined at a number, doesn't mean the limit doesn't exist at that number. So now, what trick did I say for a rational function when you get 0 over 0?
Factor out.
You have to factor out, because you see, when you plug in 2 in a polynomial, like both of them are polynomials. Inside a polynomial, when you plug in something and you get 0, doesn't that mean that you have a factor of that polynomial? So that means you can factor out these polynomials, okay? So the only difficulty is, how do you factor out the denominator, right? Well, a long time ago when I reviewed algebra, I told you, I gave you a formula for cubes, right? This is x minus 2, this is over x cubed minus 2 cubed. Whoops. Now, remember this formula that I gave you, okay? A cubed minus b cubed is a minus b multiplied with a squared plus ab plus b squared. So if I apply that, we get x minus 2 over x minus 2 times x squared plus 2x plus 4. Is everybody okay with that? Now, if you don't like to remember this formula, what can you do? How can you factorize without remembering this formula? Yeah, because you know that when you plug in 2 for x, you get 0, right? So that tells you that x minus 2 is a factor. So then you can divide x cubed minus 8 by x minus 2, long division, and then you can come up with the other factor, x squared plus 2x plus 4, okay? So keep that in mind. And now I can cancel out the x minus 2s, and whoops. Okay, so I can, after I canceled out, what I get is the limit as x going to 2 of 1 over x squared plus 2x plus 4. Now I'm going to plug in 2, because when I plug in 2, I don't get 0. So I get 2 squared plus 2 times 2 plus 4. And this is 1 over what? 12. Okay, so that's the final answer. Okay. Any questions? Do I need to go up? You guys have done that. Okay. So let's look at another one, and you're going to need this one definitely in your homework. And this is one of the reasons why, when we reviewed the algebra, I reviewed how to rationalize, okay? So you'll see that it's going to pay off now if you learned it at that time. So let's say I want to find the limit as t goes to 0, t squared plus 9 root of that minus 3 divided by t squared. So that's the limit we want to find. Notice what happens. This is not the ratio of two polynomials anymore, right? This is not a rational function anymore. But however, our goal should be similar. That is, if I plug in 0 for t, what do I get in the numerator? I get 0 in the numerator because I'm going to get root of 9 minus 3, right? And of course, in the denominator, I get 0. So once again, I'm getting 0 over 0. And what did I say about 0 over 0? Well, you try to factor out, but in this case, you cannot factor out. But then the goal should be try to get rid of the factor that gives you 0 in the denominator, right? That's the goal. So I want to get rid of the factor t squared in the denominator that's giving me 0. So in order to do that, we have to rationalize. Okay, so whenever you see root functions, and if you don't see what to do, well, rationalize and see what happens. Okay, so I'm going to rationalize the numerator here. So this is equal to the limit as t goes to 0 of t squared plus 9 minus 3 over t squared. I'm going to multiply by what? What should be after this? Plus 3. Very good. So this is t squared plus 9 plus 3. And now I have to multiply out. Now, in the last exam, some of you multiplied out in the denominator as well. When you rationalize the numerator, don't multiply out everything in the denominator, okay? Because then you might be beating the purpose, because you're trying to get rid of t squared, right? So if you multiply out, then you wouldn't be able to, cancel that out. So here's I'm going to keep the denominator as this, the limit t goes to 0, and in the denominator I'm going to write t squared multiplied with t squared plus 9 plus 3. Okay, and in the numerator, if I multiply those, I'm going to use this formula that a minus b, a plus b is the same as a squared minus b squared. You don't have to use it. If you don't use it, just multiply out by using FOIL, right? So then you are going to multiply these two numerators. You're going to get the square of this guy minus the square of the 3. And okay, so this is equal to the limit as t goes to 0. T goes to 0. In the numerator, then I get t squared plus 9 minus 9 divided by t squared times the root of t squared plus 9 minus 3. Sorry, plus 3. And this is equal to the limit as t goes to 0. Notice that 9 cancels out, right? And after I cancel out the 9s, right? If you don't mind, I'm going to do 2 steps at the same time. After I get rid of the 9s, then I have t squared and t squared, right? I can cancel them out too, right? And then all I'm going to left with is 1 in the numerator. So I have 1 over t squared plus 9 plus 3. and this is equal to, when I plug in 0 for t, this time I get what? 1 over 6. Very good. Everybody's okay. Was that? You are plugging in 0 for t, and then you get root of 9 plus 3. Root of 9 is 3, so you get 3 plus 3. Okay, everybody is okay with that. All right. Here's a fact. So let's let the limit as x going to a of f of x be equal to L, and n is and n be a positive integer, then the limit as x going to a of f of x, nth root of that, is equal to the nth root of L, so basically we are saying if I want to take the limit of nth root of f of x, it's the same as you take the limit of f first, and then you take the nth root of the limit of f, okay? And however, there is one point here that you need to remember, that if n is even, right? If n is even, then L better be what? In order for this to work, if n is even, then L better be a positive limit, right? Other, if L is a negative limit, then you cannot take the even root of that. So when n is even, here, if n is even, then we require L to be non-negative. Okay. Well, let's apply this. Let's say I need to find the limit as x going to -2 of the root of, let's say, 4th root of x to the 4 plus 3x plus 6. So I need to find the limit of this guy, and the previous fact that I gave you, it tells me that to find the limit, all I have to do is find the limit of the polynomial first, and then take the 4th root of that, okay? And do we know how to find the limit of a polynomial? Just plug in, right? Okay, so this is equal to the limit, this is equal to the limit as x going to -2 of the polynomial, and then whatever the limit is, we are going to take the square root of that. 4th root of that. and this is equal to, what's the limit? Well, we plug in -2. We know how to find the limit of a polynomial. 3 times -2 plus 6, and then we take the 4th root of that, and then this is equal to -2 to the 4 plus, yeah, that's -6 plus 6, right? So they cancel out. So -2 to the 4, so all I have is 4th root of -2 to the 4, right? The other two cancels out. What is that equal to? It's not equal to -2, okay? It's going to be +2. What you're taking is the root of 16, right? Sorry, 4th root of 16, right? And that's equal to 2. Remember, when you take root, we said we take the positive root unless I specify negative of that, okay? So in this case, the limit is 2. Everybody is okay with that. Okay, now a different kind of limit, which is limits to infinity. Okay, so limits to infinity. So what that is sometimes we are going to use the symbol, the limit as x going to a of f of x is positive infinity. And what do we mean when we write that? When we write this symbol, what does that mean? A is a number here, okay? What it means is that you can make f of x larger than any given large number by taking any x in a small interval centered at a. Okay, so any of you give me the largest number you can possibly think of, and I can find a tiny interval centered at a such that whenever I take any x there, the value of f is bigger than the number you gave me. Is that making sense? So let me write it in this way. F of x can be made larger than any given large number m, positive m, by taking any x in a suitable open interval centered at a except equal to a. Again, when I say except equal to a, it means that it doesn't matter what happens to the value of f at exactly a. What matters is what's happening to the values of f when x is near a. Okay? So in picture, what we are saying here is the following. Let's say I have a number line here, another number line here, and let's say on this number line, on the right number line, I'm going to plot I'm going to plot the values of the function, range values. And so here I'm going to plot the range value of f. Here I'm going to plot the domain values of f. I think I did the opposite previously. So let's say I pick a you give me a large number m. You give me a very large number m. And when I say that the limit of f is infinity, it means that I can make f of x to be larger than m by taking any x in a small interval centered at a, okay, except possibly equal to a. Am I making sense? So now suppose you give me a large number, I find a interval for you and see that whenever x is in that interval, f of x is bigger than m. Somebody else says, I have an even bigger number that I can imagine, and if he gives me an even bigger number, then I might have to pick a little bit smaller interval centered at a, but I can pick one like that, okay? Everybody's okay with that? All right, so that's what it means to say that the limit of f, loosely speaking, it means that as x gets closer and closer to a, from either side of a, the value of the function is going to infinity. The value is getting larger and larger. Everybody's okay? As x gets closer and closer to a, the value of the function is getting bigger and bigger. Okay. And yeah. In a suitable open interval centered at a except equal to a. When I say suitable, I mean it's by taking any x in a small enough open interval. Yeah. Yeah. Right. Yeah. So yeah. Usually I should be writing like this to make sure that what I mean. All right. So you can define this similarly, right? How would you say this? How would you define the limit as x going to a of f of x is equal to negative infinity instead of positive infinity? Can someone tell me what language you're going to use? Yes.
As x gets closer and closer to a.
From either side of a.
From either side of a.
The value of f is?
The value of f goes to negative infinity.
Yeah. So as x gets closer and closer to a from either side of a, the value of f is getting big and negative, right? So it's getting big in the negative direction. And so it means, let me just say similar. I don't like to say means similar, but is defined similarly. Now, we can also talk about the left-hand limit at a and the right-hand limit at a being negative infinity or positive infinity, okay? So all I'm going to say is similarly for similarly defined. Okay, so I'm going to give you a bunch of limits here. One, the limit as x going to a from the right of f of x is equal to infinity. 2, the limit as x going to a from the right of f of x is equal to negative infinity. 3, the limit as x going to a from the left of f of x is equal to positive infinity. 4, the limit as x going to a from the left of f of x is negative infinity. So the first one means as x gets closer and closer to a, from the right side of a, the value of the function is getting bigger and bigger, right? And similarly for the other ones. Everybody understands what I mean by similar, right? Okay. Let me go over a few examples now. Yeah. Okay. Let's go over a few examples and make sure we understand this. My first example is the following. What's the limit? What's the limit as x going to 0 of 1 over x? So first of all, if the limit exists as a number, we say that the limit exists. If the limit does not exist as a number, then we check whether the limit is infinity or negative infinity. If the limit is not either, then we say that it doesn't exist at all, even as infinity or negative infinity. So here, what should be the limit here? Anyone remembers? The graph of 1 over x looks like what? Well, on one side it looks like this. On the other side it looks like this, right? So what is happening at 0? What's the limit at 0? Well, I would say that this two-sided limit does not exist. Okay? First of all. However, we could say the following, that the limit as x going to 0 from the right. So if I ask you what's the limit at 0 of 1 over x, you'll say that it doesn't exist. But if I ask you what's the limit at 0 from the right, then what would you say? It's not plus or minus, it's infinity. And if I ask you what's the limit as x going to 0 from the left of 1 over x, then you'd say that it's negative infinity. Okay? Everybody's okay with that? So when the limit of a function at a point is infinity or negative infinity, it basically means that you have a vertical asymptote there, right? When the limit of a function at a point is infinity or negative infinity, it means that you have a vertical asymptote at that point. Everybody's okay with this? Let's look at another example. Let's say that I need to find the limit as x going to 0 of 1 over x squared. Okay, anyone knows what this limit is? Anyone knows the limit? Anyone knows the limit? Yeah, so the graph of this guy, it looks like the following, okay? It is similar to 1 over x on this side, but when x is on the negative side, now because 1 over x squared is always positive, now you get that this is the same as Okay, so that's what we have. That's how the graph of 1 over x squared looks like. So this limit is what? The two-sided limit is infinity, right? Everybody is okay with that? You guys are okay? All right. Now, notice that in both cases, right? In both cases, let me talk about the first case. In the first case, what is happening? The denominator is getting closer and closer to 0, right? The denominator is, first of all, notice that this fraction, when x is close to 0 on either side of 0, when x is close to 0 on either side of 0, 1 over x squared is always positive, right? Okay? And then, when x is close to 0, the value of the fraction is big, right? Think about dividing 1 by 0.000000001. How many zeros I said? I don't know, but what is that? It's a big number, right? For example, if you divide 1 by, say, 0.001, what do you get? You get 1,000, right? 1 divided by 0.0001 is 1,000. So 0.001 is 1,000. So if you divide 1 by smaller and smaller numbers closer to 0, then you get bigger and bigger numbers. Right? That equation is important. What's happening with these two? Notice that in this case, when x is close to 0, on the right side of 0, right? Then 1 over x is positive or negative? Positive. When x is close to 0, on the right side of 0, 1 over x is positive. But because I'm dividing 1 by smaller and smaller numbers, the fraction is getting bigger and bigger. That's why I'm getting infinity, okay? In this case, I'm trying to talk about this without the graph. What's happening here? Well, the limit of 1 over x, and when x is close to 0, on the left side of 0, what's the sign of 1 over x? 1 over x now is negative, right? If x is close to 0, on the left side of 0, it simply means that x is negative, right? So in this case, x is negative, so this fraction will be negative. However, we are dividing 1 by a number which is close to 0, so the fraction will be big, so you get negative and big. That makes sense? So, keep these two ideas in mind when I do the next problem. Because I'm not going to be drawing any more graphs. So here's an example. Let's say I need to find the limit as x goes to 3 from the right of 2x divided by x minus 3. Okay? Now, let's see what's happening here. What's the limit of the numerator when x is getting closer and closer to 3? See, as x gets closer and closer to 3, the numerator gets closer and closer to 6. But the denominator is getting closer and closer to 0, right? The question is, what's the limit? Okay. Now, first of all, realize the following fact, that notice that when x is close to 3, the numerator is almost not close to 6, right? But then the denominator is very, very close to 0. So when you divide 6 by something very, very close to 0, wouldn't you get something big? I mean, imagine dividing 6 by 0.001 again, you're going to get 6,000, right? Everybody's okay? 6 divided by 0.001 is 6,000. So then, My answer should be infinity or negative infinity, because if whenever you have a fraction, right? Whenever you have a fraction, the limit of the numerator, let's say, is a fixed number. The limit of the denominator is 0. Then the limit of the ratio would be plus or minus infinity. Am I making sense? Now, which one is it? Well, why? Because of the following. Notice you need to figure out what's the sign of the fraction when x is close to 3 on the right side of 3. What's the sign of the fraction when x is close to 3 on the right side of 3? So here is let's say 3, and x is going to 3 from the right side, right? So doesn't that mean that x is bigger than 3? So when x is close to 3 on the right side of 3, the denominator x minus 3 is positive, right? Well, then the fraction, because when x is close to 3, the numerator is close to 6, it's positive. When x is close to 3, the denominator x minus 3 is close to 0, but it's positive because x is greater than 3. So together, the fraction when x is close to 3 on the right side of 3, the fraction is positive, and because I have 0 in the denominator, this limit would be positive infinity. Everybody's okay? Now, what I said here wouldn't work if the numerator is also 0, right? We already looked at what to do when I get 0 over 0, right? We already looked at that before. Now, can someone tell me very quickly what's the limit as x going to 3 from the left side, 2x over x minus 3? What is that limit? Negative infinity. And if I ask you what's the limit as x going to 3 of the same fraction, what did you say? It does not exist. Okay. All right. Okay, what I want to do next is I want to review the graphs of the trig functions because we are going to need them now. So I'm going to start with the sine function and then show you the graphs of the other ones, and you have to remember this graphs, okay? Let's start with the graph. So let's say I want to know the graph of the sine function. So let me say example, sketch the graph of the sine function. Now, the sine function is periodic with period 2, right? The period 2 pi. Because if I have sine of, so recall the following, sine of theta plus 2 pi or minus 2 pi is the same as sine theta. So this is why we say the sine is periodic with period 2 pi. So it means that in terms of graph, if I know the graph of sine between 0 and 2 pi, if I know the graph of sine between 0 and 2 pi, I know the graph of sine everywhere, because all I have to do is repeat that in both directions. Okay? Repeat that in both directions. So, first of all, let me remind you that let's say this is a circle, this is the unit circle, So this is the unit circle, and remember, for any angle x, the coordinates of this point is given by what? The first coordinate of this point is cosine x. The second coordinate is what? Sine x. So because sine x represents the second coordinate, sine x represents the second coordinate of the point on the unit circle, so then sine x, the value of sine x is always between -1 and 1. Okay. Now I'm going to show you the behavior of the sine function in terms of where the sine function increases, where the value of the sine function decreases. Okay. So I'm going to make a picture here for the sine function. Let's say I have the let's say this is here 0, this is here 2 pi. So in the middle here I'm going to have pi, right? Right here I'm going to have the number pi over 2. Right here I'm going to have the number 3 pi over 2. Now notice, what is the value of sine? What's the value of sine x when x is 0? 0. What's the value of sine x when x is pi over 2? 1. So what's happening between 0 and pi over 2? Remember, I have the circle, and the value, notice that when x is the angle 0, the point is, what point do I get? 1, 0, right? So sine 0 is 0. And then as you increase the angle from 0 up to pi over 2, the value of sine is increasing, right? Because the value of sine represents this vertical length, right? So as you increase the angle from 0 to pi over 2, the value of sine is increasing from 0 to 1. Okay? So it increases from 0 to 1. Okay? Now as you go from now pi over 2 to pi, then what's happening? It decreases to what? 0, because now when sine pi is 0, what is happening from pi to 3 pi over 2? Even decreasing from 0 to -1. So this is -1 here, and it's decreasing up to -1. And then between 3 pi over 2 to 2 pi, it goes back up to 0. Everybody's okay? So that's the behavior of the sine function. So I'm going to use that to draw the graph of this sine function. You guys are done writing this down? Okay. I need space, so I'm going to get rid of that. Let's try to draw the graph of sine function. Okay, let's say I need to pick a height for, okay, let's pick this height to be 1. Okay, so I'm going to pick 1, 2, and 3. Pi is about 3, right? 3.14. 3, 4, 5, and 6. So I'm going to say that my pi is about here, and 2 pi is about here. Okay, what's the value of so we know that the value of sine at 0 is 0, right? The value of sine at pi is what? 0. The value of sine at 2 pi is 0. Okay, what's the value of sine at pi? This is where pi over 2 is, right? This is where pi over 2 is. What's the value of sine at pi over 2? 1. What's the value of sine at 3 pi over 2? Negative 1. Okay, so the graph looks like the graph of sine between 0 and 2 pi looks like this, and which makes sense with our investigation that sine increases from 0 up to 1, right, and then it decreases to 0 up to pi, and then after pi it's decreasing to negative 1, and then it's increasing from negative 1 to 0, right? So it matches that. Now this is the graph between 0 and 2 pi, but what's the graph between everywhere? Well, you repeat this. You repeat this in both directions. Okay. So let me try to do that. Maybe right up here. What's that? Oh, this is on the other side. Yeah. Yeah. Okay. So this would be like this, and then okay, and also it's going to repeat right here. Okay. Is everybody okay? So you take the part that you have between 0 and 2 pi, you shift it right here. Okay, all you're doing, you're shifting it right here. You're not reflecting it. You're not reflecting it. It's important. You're shifting it to the left by 2 pi units. Yeah.
And this is where plus or minus 2 pi gives you the same thing, right?
Yeah, because it's periodic with 2 pi, that's why you do that. Yeah. Okay, so that's the graph of sine. Can someone tell me though, what's the graph of cosine? Yeah, so let me just say a couple of things here. Red means I'm thinking about cosine, okay? So what is happening to cosine of x? Cosine of x represents the first coordinate of the point, which is the intersection of the terminal side of the angle and the circle, right? So what is cosine of 0? Cosine of 0 is 1. And then on the circle, cosine 0 represents which length? Cosine 0 represents this length here, right? So when the angle is 0, cosine x is 1. And then as the angle goes up to pi over 2, this length is shrinking to 0, right? Okay? What is happening between pi over 2 and pi? This length is increasing in the negative direction, right? So it's going from 0 to negative 1. And so if you do that, what you're going to get is getting 1 here, and then the cosine value you set is 0 here, right? So it decreases up to 0. And then what's the cosine value at pi? Negative 1. So that means it's decreasing even more, right? And then between negative 1 and 3 pi over 2, it goes up to 0. And then here it goes up to what? 1. So use that to come up with the graph. So cosine 0 is what? Cosine 0 is 1, sorry, right here. Okay, let me... cosine 0 is 1, this red dot. And cosine of pi over 2? 0. And cosine of pi? Cosine of pi is negative 1. Cosine of 3 pi over 2? 0. Cosine of 2 pi? 1, right? So what am I getting? And here, what's going to happen? At negative pi over 2, it'll be 0. Okay? And then it's coming to this point here. Is that making sense? Again, it's going to extend in both directions. Okay. So the red one is cosine x. The green one is sine x. The green one is sine x. Everybody understands the graphs of these two functions. Is that okay? All right. Now let's answer a couple of questions. If I ask you what's the limit of sine x as x goes to 0, what did you say? What's the limit of sine x as x goes to 0? What's that? 0, right? What's the limit of cosine x as x goes to 3 pi over 2? 0. What's the limit of sine x as x goes to 3 pi over 2? Negative 1. Okay. So if you know this graph, you can answer the limits about these two functions very easily. Right now what I'm going to do is I am going to show you how to obtain the graph of secant x. Okay. And for that, I am going to delete my sine function. Okay. So, which is a little bit depressing, but you know what? I'm going to make the graph of cosine once again, okay? And show you how to obtain the graph of secant, okay? So here is my x-axis, and here is my y-axis. Here is what I get. Okay, I think we were getting 1, 2, 3, 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Okay, so the graph of cosine, this is where pi is for me, this is where 2 pi is for me, and this is in the middle right here would be pi over 2. So right here would be pi over 2. So I'm going to get something like this here. And at pi, the value is -1. And where is 3 pi over 2? 3 pi over 2 is right here. And at 2 pi, the value is 1 again, right? So that's how it looks like there. What's happening here? I have to see where 1, 2, 3. So the negative pi is right here. So I go up to this point, and where is 3 pi over 2 would be right here, and this is how it looks like, right? So let me label the points again. This is 3 pi over 2 right here. This is 0. This is negative pi over 2. This is negative pi. This point here is negative 3 pi over 2. This point here is negative 2 pi. Everybody's okay with that? This is the graph of cosine. So this is the graph of oops. This is the graph of cosine x. Now, I want to draw the graph of secant, right? Notice that what is secant? Secant is 1 over cosine, right? So let me use green here. So I want to draw the graph of secant. And secant I know is 1 over cosine. Not reflection. Not reflection. Not reflection. So notice that whenever x is a multiple of odd multiple of pi over 2, cosine is 0, right? So at pi over 2 cosine is 0, right? At negative pi over 2 cosine is 0. So then I am for secant I have to divide 1 by 0, right? What does it tell you? Well, it tells me that that the value of secant would be very big near those points, right? So if I make a line here, so this would be vertical asymptotes. This would be vertical asymptotes for secant. My scales are obviously bad, but we're going to work with that. So the secant, what's the value of secant when x is 0? When x is 0, what's the value of secant? 1. So I get the point right here. But then when x is near, so when x is near pi over 2, cosine x is near 0, right? But positive. Cosine, when x is near pi over 2 on the left, when x is near pi over 2 on the left, cosine x is near 0 but positive, so that the value of the secant will blow up to infinity right here. Same thing happens when x is close to negative pi over 2 on the right side of pi over 2. Looks like a parabola, yeah, but it's not quite, yeah. Okay, so what's happening? What's happening then? Okay, what's going to happen? What's going to happen here and here? What's going to happen? What's the graph of secant in here? Well, secant of pi would be what? Secant of pi would be negative 1 as well, right? And then the graph when x is close to pi over 2 on the right side of pi over 2, now cosine is 0 but negative. So now you get this. Okay? And you keep doing that. You keep doing that for all the other intervals, okay? Am I making sense? Is everybody okay with that? What's that? Yeah, so what I'm saying here, first of all, when x is close to pi over 2, on the right side of pi over 2, what's the value of cosine? When x is close to pi over 2, cosine is close to 0. So 1 over cosine will be big, because you're dividing 1 by a very small number. So when x is close to 0, cosine x is close to 0. So 1 over cosine would be big. Okay? Same thing happens here. When x is close to negative pi over 2, on the right side of negative pi over 2, the cosine x is close to 0. So 1 over cosine would be big. Okay? And similarly, same thing is happening here. Okay? This is the graph. The green one is the graph of secant. Of course, I didn't draw the entire graph. You have to repeat this everywhere. Now, usually you need to know. Usually, it's enough to know the graph of secant between negative pi over 2 and 3 pi over 2. Okay, for most of the purpose. For most purposes. Say it again. Oh, so now what would be the graph of secant between negative pi over 2 and negative 3 pi over 2? It would be like this. Okay. Now let's answer a couple of questions. What's the limit of the secant function as x goes to pi over 2 from the left side of pi over 2? So everyone is done drawing this, sketching this? You guys are done sketching this? Okay, let's answer a couple of questions now. What's the limit as x going to pi over 2 from the pi over 2 from the, did I answer that? Let's say from the right side of this secant of x. What is this limit? Yeah, so all I have to do is look at my graph here. I see that when x is close to pi over 2, when x is close to pi over 2, on the right side of pi over 2, secant is negative infinity. Is that making sense? What's the limit as x going to pi over 2 from the left side of pi over 2 of secant x? That's positive infinity. And you can answer other questions as well, right? What's the limit at pi? What's the limit of secant at pi? What's the limit of secant at pi? What's that? The limit of secant at pi. Negative 1, right? Okay, so yeah, from both sides, yes. So the limit is x going to pi of secant x is negative 1. You guys can handle limits involving trig functions, okay? Now, how would you sketch the graph of cosecant, you think? Yeah, except that you're going to now work with the graph of sine, right? The graph of cosecant, and let me just show you one step there. The see, wherever sine is 0, cosecant will have a vertical asymptote, okay? So the graph of cosecant will be this blue curve, okay? This blue curve will be the graph of cosecant, right? Because cosecant is 1 over sine, so wherever sine is 0, cosecant will blow up. Okay, so I'll let you draw the graph of cosecant yourself. The graph of these functions are also given in the back of your book, textbook, which is Appendix D. Okay, so now, the one more thing that we need is the graph of tangent. Okay, what's the graph of tangent? Yeah. Whoops. Are we looking at cosecant or? Yeah. It's really important that these pictures that I'm giving you, when you go to calculus 2, right, they have to be in your head. Okay, believe me or not, because you're going to be talking about inverse trig functions, and there, when you go there, you have to know the graph of inverse cosine, inverse sine, inverse tangent, inverse secant. Okay, so many graphs. So you better memorize these graphs right now. Okay, it's really it's going to make your life easier if you just remember these graphs. Okay, instead of trying to come up with them. Okay. Okay, you guys feel like you need a break right now? Okay, let me finish the tangent and then I'll give you 5 minutes, okay? So here's the graph of tangent. Okay, let's say this is where, no, I'm not going to be that much precise now. This is, let's say this is pi over 2. This is pi, then this is 3 pi over 2 then, and this is 2 pi then, right? And in the negative direction I have about the same distance. Is it negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay. Okay, now remember what is tangent. Tangent of x is the same as sine x divided by cosine x. Okay? Now, one thing you need to realize that sine x and cosine x will never be 0 at the same time. Why? Because sine is 0 whenever the terminal side is on the y-axis. Sorry, whenever the terminal side is on the x-axis. And cosine is 0 whenever the terminal side is on the y-axis. So they cannot be 0 at the same time. Now, when will tangent be 0? Well, the tangent will be 0 whenever sine is 0, right? Because sine is on the numerator. Tangent is 0 whenever sine is 0. So tangent is 0 when sine is 0, right? Right here. Another thing that you want to notice, so tangent will be 0 at multiples of pi. Whenever you have a multiple of pi, tangent will be 0. Now, you have cosine in the denominator, right? So cosine could be 0, right? When is cosine 0? Cosine is 0 at pi over 2, right? And so the value of tangent will have, so the tangent graph will have a vertical asymptote at pi over 2. Okay? Same thing happens at negative pi over 2. So let me draw that. So I'm going to first look at what's happening between negative pi over 2 and pi over 2, okay? So let's investigate. When x is close to pi over 2, on the left side of pi over 2, the cosine x is close to 0, but it is positive, right? You have pi over 2, and when x is going to pi over 2, the cosine x is positive, but it's close to 0. So the fraction will blow up, okay? So that means the graph looks like this. That the graph, oops, how do I make it nicer, I guess? Like this. And then when x is close to negative pi over 2, okay, negative pi over 2 from the right side of negative pi over 2. So think about negative pi over 2 is like, here's the circle and here's the x-axis, negative pi over 2 is here, right? So there, cosine of those are positive, right? Because when x is close to negative pi over 2, on the right side of negative pi over 2, it means the angle is in the fourth quadrant. So cosine x is positive and close to 0. However, sine is now negative, right? So that's why you're getting negative infinity here. Okay, so that's how the graph looks like between pi over 2 and negative pi over 2 and pi over 2. Now, what's happening beyond that? Well, the same thing is going to repeat. Okay, so for example, This is pi over 2, and this is where you have 3 pi over 2. So this is where you have 3 pi over 2. This is where you have pi over 2. So okay, so here is this is where pi, okay, this is pi and this is 3 pi over 2. So what's happening between pi over 2 and 3 pi over 2? Well, same thing. You are going to go like this, and then you're going to go like this. Am I making sense? The same thing happens between pi over 2 and 3 pi over 2. Everybody is okay? Making sense? And again, what's happening beyond that, and so on. In calculus 2, it's important to know the graph of tangent between negative pi over 2 and positive pi over 2. If you know that most of the time, that's enough. Okay, but you should know in general how the graph of tangent looks like. Everybody's okay? All right. So when you go to calculus 2, you can't say that your instructor didn't talk about the graph of tangent. Well, even if you say that, there is no excuse because you're supposed to know it from high school. Okay. Now, somebody tell me what's the limit as x going to pi over 2 from the right side of pi over 2 of tangent of x. Yeah, from the right side it's negative infinity, and from the left side it's I have to write tangent. Positive infinity. Okay, I think after sketching all these graphs, my hand is a little bit tired. Okay, so let's take exactly 5 minutes break and then we will resume. Okay. Resume the lecture. Okay, there are two general facts that I want to give you now. One is the following. If the value of f of x is less than or equal to the value of g of x for x near a, except possibly at a, except possibly at a, and if the limits of f and g exist at a, then we can say that the limit as x going to a of f of x is less than or equal to the limit as x going to a of g of x. Loosely speaking, if f is less than g near x, near a, then the limit of f would be less than the limit of g. This works for left-hand limits and right-hand limits as well. If you think about the graph, right, because f is smaller than g near a, so near a, the graph of f would be above the graph of g, right? So obviously the limit of f would be bigger than the limit of g. Is that making sense? Okay. Are you done writing it down? Yeah. Is this statement clear to you guys? Okay. So just think about the graphs of the two functions. The assumption is basically when x is near a, the graph of f is below the graph of g. So therefore the limit of g would be bigger than the limit of f. So what I'm saying is that let's say this is the x-axis, and let's say this is a, and so the graph of, let's say, the graph of f near a, and the graph of g near a. So this one is the graph of g. This one is the graph of f. My point is, we don't care what happens at a. At a, whatever happens doesn't matter. Maybe at a, the value of f is bigger than the value of g. Okay, it doesn't matter. The graph of f is below the graph of g when x is near a, and so the limit of g at a would be bigger than the limit of f. Okay, so that's obvious if you think about that in terms of the graphs. The next theorem is the one that we are going to use later. This is the theorem, and it has a very weird name. It's called the squeeze theorem. Squeeze theorem. People use another name for it. Some people call it the sandwich theorem. Okay. So what it says is the following: if f of x is less than g of x is less than h of x when x is near a, except possibly at a, and the limit as x going to a of f of x is equal to L, and also the limit as x going to a of h of x, then the limit as x going to a of g of x is L as well. So basically, the function g of x is bounded below by f and bounded above by h. So if you think about it, the graph of h is above the graph of g, and the graph of g is above the graph of f. Okay? And what we are saying, if f and g, they have the same limit, then the middle one must have the same limit. If f, g have the same limit, then the middle one must have the same limit. And graphically, what's happening is the following. I'm not going to bother drawing x and y axis. Let's just say, for me, f is the most f is the one which is below all the other ones. So let's say the graph of f. Let's say this is the point at a, okay, and the graph of h. The graph of h is, so this is the graph of h. This is the graph of f. We don't know what's happening exactly at a. This is the point at a, okay? Maybe at A the functions are not defined, or maybe they are defined at different points. But the graph of H and graph, because H and F, they have the same limit at A, right? So then maybe I'll draw these x-axis here. Let's say. So here's what A is. Okay, here's A, and the limit here. Okay, so the limit here is L. Okay, the limit here is L. So if F and H, they have the same limit, what's G? Well, G is in between the two, right? So the graph of G must be in between the two, right? So wouldn't that force the graph of, wouldn't that force the limit of G to be L as well? So whatever G is, G has to be in between. So at A, the limit of G must be L as well. Okay? That's what's going on. Is everybody clear? Okay. Let's use an example to illustrate how to use the squeeze theorem. Suppose that I need to know the limit as x going to 0, x squared multiplied by sine 1 over x. Okay. When x is 0, this function is undefined because you have 1 over x there. And so how do I find this limit? Well, what I'm going to do is I'm going to start with sine 1 over x. And we are going to, first of all, say that the value of sine 1 over x is between what? Between 1 and sine value, no matter what the angle is, sine is always between -1 and 1. So the angle is 1 over x, whatever x is, the value is between -1 and 1. Now I'm going to multiply everything by x squared. So this would be -1 times x squared is less than x squared multiplied by sine 1 over x is less than or equal to 1 times x squared. So I am multiplying everything by x squared. So what happened then? Well, our function is between negative x squared and positive x squared, right? Now, can someone tell me what's the limit? What's the limit of this guy when x goes to 0? 0. When x is close to 0, the limit of x squared is close to 0. What's the limit of negative x squared when x is close to 0? 0 as well. So the limit of the upper bound is 0, the limit of the lower bound is 0. So the limit of the middle one is? So the limit of this one would be 0. So this limit would have to be 0 as well by this squeeze theorem. Yeah.
Even though there's a 0 in the denominator?
Yeah, this function is undefined at 0. Okay. But that doesn't mean that the limit doesn't exist.
Okay.
So a function may be undefined at a number, but the limit may exist.
So we use those two at 0 to figure out that.
Yeah. Well, the squeeze theorem says if you have, so our function is bounded above, bounded below by two functions, and the limit of both functions are 0. So the limit of the middle one will be 0. That's what the squeeze theorem said, right? Am I making sense?
Yeah, I'm just trying to figure out how you jump from your equation to your first.
Well, this is what I started with. I'm saying the sine function I know to be between -1 and 1, and then if I multiply out everything by x squared, I see that this x squared sine 1 over x is in between these two functions. These two parabolas, right? In between these two parabolas. So because this function is in between, and if they have the same limit at zero, then the middle one must have the same limit at 0. So these two guys, they have the same limit at 0. So the middle one should have the same limit. Let me draw the graph of this to illustrate what's going on here. Let me make my x-axis right here, my y-axis right here. Okay, let's see how the parabolas look like, right? What's the graph of x squared? The graph of x squared will be a parabola which is like this, right? And what's the graph of negative x squared? The graph of negative x squared, the graph of negative x squared will be like this, right? Everybody's okay? And then the graph of our function would be where? See, our function x squared sine 1 over x is in between negative x squared and positive x squared, right? So the graph of our function x squared sine 1 over x will be where? Will be in between, okay? And actually the way it looks like is this. The graph of x squared sine 1 over x. Okay? There is a hole because it's undefined at 0. But then otherwise it looks like this. Okay, so this is the red one. So the red one is the graph of x squared sine of 1 over x. You don't have to know the graph. And this is the graph of x squared, and this is the graph of negative x squared. That's how the graphs look like. Okay, again, the graph is not part of the solution. All you have to say is what I said before. If you want to use the squeeze theorem, then whatever function you have to show that that function is in between two other functions, and the two other functions, they have the same limit, forcing the limit of the middle one to be the same. Okay? Is everyone doing okay with that? Okay, so go up. Yeah. Right there. Just the graph. Okay, we are done with section 1.5. You should be able to do all your homeworks in that section now, okay? When you do your homework, keep in mind the guidelines that I said for what happens, what to do when you get 0 over 0, what happens when you get something divided by 0, things like that. Just keep those in mind when you do your problems. Okay. Let me know if you're done writing it down. What I'm going to do now is, it might be surprising for you, but I'm going to skip to section 3.4, no, not 3.4, section 4.4, I think. The reason is the text decided to talk about another kind of limit in a later section. But I think that since I talked about limits so much already, why not just talk about that last kind right now? And then when we get there, we'll say that we were done with that before, okay? So I will talk about section, I think, 4.4. I'll identify that later and finish up everything about limits right now, okay? Oh, I think I have the text with me, so I can check very quickly what section it's at. Section 3.4, okay, section 3.4. So this is section 3.4. Okay. So section 3.4 is about limits at infinity. Okay, limits at infinity. Remember, the last thing that we did was limits to infinity, right? Limits to infinity. Now we are saying limits at infinity. So what are we going to talk about here? We are going to write this symbol, the limit, as x going to infinity of f of x is equal to L. So what does that mean? What does that mean? So this means that f of x can be made as close to L as we desire by taking any x larger than a suitable large number. Let's say suitable large number, what should I use? Let's say n, capital N. Okay, so let me explain to you what it means here. So here I'm going to be sketching, let's say this represents the range of f and this represents the domain of f. What we are saying is the following. These are copies of a real number line. Let's say I have L here. We are saying that we can make the value of f to be as close to L as we desire simply by taking any x larger than a big number n. So if x is bigger than n, f of x is very, very close to L. Okay? Am I making sense? So I can make the value of f of x to be as close to L as I desire by picking any x larger than a suitable large number n. Okay? So if I say that loosely, what I'm going to say is that as x gets bigger and bigger in the positive direction, as x gets bigger and bigger, the value of the function is getting closer and closer to L. Okay? So I'm going to give you some examples and explain what's going on here. What's the limit as x going to infinity of 1 over x? Well, since I have the sketch of the function 1 over x, I'm just going to go there and use that instead of drawing it again. This was the graph of 1 over x. So as x gets bigger and bigger, the value of this function is getting closer and closer to 0. Okay? So this graph is getting if you look at the graph of 1 over x, this part is getting closer and closer to the x-axis, okay? So the limit of 1 over x as x goes to infinity is 0, which sort of makes sense. If you think about it, what we are doing is we are dividing 1 by bigger and bigger number, right? We are dividing 1 by bigger and bigger number. Obviously, the ratio is getting closer and closer to 0. Now, I'm going to ask you the same question. What's the limit of 1 over x as x goes to negative infinity? As x goes to negative infinity, realize that the value of the function is getting closer and closer to 0 as well. What you're doing here is basically you're dividing 1 by bigger and bigger negative number, right? But again, the ratio will be very, very small, right? Close to 0. Am I making sense? Think about dividing 1. What is 1 divided by negative 1,000? What is 1 divided by negative 1,000? Negative 0.001, right? So that gives you the intuition to say this limit is 0. And in fact, if I look at the limit as x going to negative infinity of 1 over x, that's 0 as well. What's the limit as x going to infinity of 1 over x squared? What is that limit? Well, again, it's 0, right? Because we are dividing 1 by bigger and bigger numbers. And if we look at the graph of 1 over x squared, where did I? Yeah. This is. No. This is the graph of 1 over x squared. So as x goes to infinity, this guy goes to 0. As x goes to negative infinity, the value goes to 0 as well. So this is 0. Even if x goes to negative infinity, 1 over x squared goes to 0. Okay, pay attention to what I say now. Suppose you have a ratio. You're taking the limit of a ratio. Suppose that the limit of the numerator is a fixed number. The limit of the numerator is a fixed number. The limit of the denominator is infinity or negative infinity. Okay? Then the limit of the ratio would always be 0. Am I making sense? Let me write that down here like this way. Suppose you're trying to look at the limit as, so let me say this is a remark. Suppose you're looking at the limit as x going to x going to, well, suppose you're looking at the limit of a ratio, okay? And a limit is going somewhere, okay? And suppose that the limit of the numerator is a fixed number. It's a fixed number. And the limit of the denominator is plus or minus infinity. Okay? The limit of the numerator is a fixed number. The limit of the denominator is plus or minus infinity. Then this limit would be what? 0. I mean, imagine that when you're dividing almost a fixed number by bigger and bigger numbers. Okay? So that's why the limit would be 0. You can remember that? You're going to need that when you do the problems, okay? Yeah. So remember, when I had 1 over x, basically the limit of 1 is 1, the limit of x is infinity, so 1 over that goes to 0. Okay? I'm going to do examples. This will be made clear. Here is an example. What's the limit as x going to infinity of 1 over x to the r, where r is positive, let's say? What is this limit? R is a fixed exponent, okay? R is like having half or 2 or 1.5. Well, since r is positive, it's still what's going on here is that the limit of the numerator is what? The limit of the numerator is 1 because it's just 1. The limit of the denominator though is what? As x goes to, when x is big, x to the power r is also going to be big. So as x goes to infinity, x to the r is also going to infinity. I mean, think about x to the r at x squared or x to the half. Okay? What is the graph of x to the half? Actually half looks like this, right? So when x goes to infinity, the value of actually half goes to infinity. Okay? Am I making sense? So here this guy goes to 1, this guy goes to infinity, so the ratio goes to 0. Okay? Is everybody okay with that? Okay. Example. Suppose I want to find the limit as x going to infinity of 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. Let's say I want to find this limit. What's the limit of the numerator? What's the limit of the numerator? Anyone? What's the limit of the numerator? Yes? I'm just asking what's the limit of the numerator part as x goes to infinity. Think about this. We are talking about when x is big. When x is big, this guy is the dominating term, right? Because when x is big, x squared is so much bigger than both of these terms, right? So when x is big, this whole thing would be very, very big. Am I making sense? So if you are looking at the value of a polynomial, and you want to know what's the value of a polynomial when x is big, it only depends on the leading term. Okay? The leading term is the dominating term. Okay? So when x is big, this guy is much bigger than these two guys. Okay? So that's why the limit of the numerator would be infinity. Because when x is big, x squared is big. Right? Same way, what's the limit of the denominator? Infinity as well. Okay. In fact, let me make this negative 5. Okay. Then this would be what? Negative infinity, because I have negative 5x squared. So what's the limit? What's the limit of the ratio then? Okay. I was hoping someone will say that, and so that I can say wrong, and so that I can be dramatic about it and try to make you remember this. Just because you have infinity over infinity doesn't mean that limit is 1. Just because it's negative infinity over negative infinity doesn't mean it's negative 1. Let me give you some silly examples to remember why that's the case. Okay, so here's some silly examples. First, let me use a different color. So let's think about this. What's the limit as x going to infinity of x divided by x? Notice that the limit of the numerator is infinity, limit of the denominator is infinity, right? And in this case, indeed, the limit is 1, right? Because x divided by x is 1. Is everybody okay with that? Oh, actually, everybody's okay with that? However, let's say I have put a 2 here now, right? What's the limit now? The limit of the numerator is still infinity. The limit of the denominator is still infinity. However, what's the limit? It's not 1, right? Because x cancels out. 2x over x is in fact 2 in disguise, right? So this limit is in fact just 2. It's not 1. Okay? Another silly example. Let's say I have the limit as x going to infinity of x divided by x squared. And again, what's the limit of the numerator? Infinity. What's the limit of the denominator? Infinity. However, what is this limit? X divided by x squared is what? 1 over x, right? And 1 over x has limit what? 0 as x goes to infinity, right? x divided by x squared is just 1 over x. So 1 over x goes to 0 when x goes to infinity, right? Is everybody okay with that? Just to give you one more example, let's say I want to know what's the limit as x going to infinity of x squared divided by x. Now what happens? Again, I have infinity over infinity, but the limit is not 1. The limit right now is what? X squared divided by x is in fact what? Just x. So as x goes to infinity, x goes to infinity, right? This time I have infinity. Am I making sense? So when you say it again? Last one? Yeah, I'm saying the numerator goes to infinity because when x is big, x squared will be big. The limit of the denominator is also infinity when x goes to infinity. But the limit of the ratio is not 1 because x squared divided by x is just x, right? X squared divided by x is equal to x. So you're taking the limit of x, and the limit of x is infinity. Yeah. Yes, we're going to get there, right? Okay, so what's the limit of the blue function that I had? Well, the trick is whenever you are taking the ratio of two polynomials and you're looking at the limit at infinity or negative infinity, what you need to do is factor out the leading term. Factor out the leading term. So for this problem that we had, you have the problem with you, right? So I'm just going to go here. So now look at the blue function. The limit as x going to infinity, 3x squared minus x minus 2 divided by negative 5x squared plus 4x plus 1. So what I'm going to do is factor out the leading term. And if I factor out the leading term, I get 3 minus, what do I get? 3 minus 1 over x minus 2 over x squared, right? And then in the denominator, if I factor out x squared, I get negative 5 plus 4 over x plus 1 over x squared. You guys agree with that? If I factor out x squared from the numerator and the denominator, then I'll be left with those. Now I can cancel out x squared. Now let's ask ourselves the following question. What is the limit of this guy as x goes to infinity? What's the limit of 2 over x squared when x goes to infinity? 0, because the denominator is becoming big. What's the limit of this guy as x goes to infinity? What's the limit of this guy? What's the limit of this guy? 0. So what am I left with? I am left with 3 over negative 5. Okay, so that's negative 3/5. Everybody's okay? Is this making sense? So anytime you have the ratio of two polynomials and you need to find the limit as x goes to infinity or negative infinity, what you need to do is factor out the leading term and then think about what's happening when x goes to infinity. Okay? You guys understand that? Any questions on the algebra? When you factor out x squared, you realize that you're going to get what I have inside the parentheses. Everybody's okay with the algebra? Okay, let's do another example like this. This time, let's take the limit as x going to infinity, 2x squared plus 1, the root of that divided by 3x minus 5. Okay, once again, what you have is when x goes to infinity, the numerator goes to infinity. When x goes to infinity, the denominator goes to infinity as well, right? Once again, the limit is not 1. Now, how do I figure out the limit of this guy? Well, even though I don't have a polynomial in the numerator, I can still apply the same trick. Okay? So you take the limit as x going to infinity. In the numerator, I'm going to factor out x squared, so I'm going to get 2 plus 1 over x squared, and then I have the square root here. And in the denominator, I am going to factor out x, and then I have 3 minus 5 over x. You guys agree with that? Now I am going to rewrite this as square root of x squared would be just x, because x is going to infinity, I can assume x is positive. Okay, and then I get the root of 2 plus 1 over x squared, right? You guys agree with that? Basically what I should be having is this, right? Root of x squared times the root of 2 plus 1 over x squared, and here I get x times 3 minus 5 over x. Everybody's okay with that? Now root of x squared and x, they will cancel out, right? This will cancel out this x here because they are the same. So now as x goes to infinity, what is happening to this guy? 0. This guy is 0. So I am left with what? Root of 2 over 3, right? Root of 2 over 3. Everybody's okay? Yep. Okay, now I am going to be talking about one more type of problem. Sometimes you have the difference of two. So sometimes what happens is that, let me say that as a remark, sometimes you are taking the limit as x going to somewhere of f of x minus g of x, and what happens is that f of x goes to infinity and g of x goes to infinity as well. So what you have is infinity minus infinity, right? So each you have the difference of two functions, and each function goes to infinity. The question is, what's the limit of the difference? What's the limit of the difference? Anybody? Oh, I'm saying, do you have an answer for what should be the limit? Okay, once again, I'm very happy that you said 0 so that I can say it wrong, and then I can be dramatic about it. Now, the reason I was hoping that you'll say the wrong answer is that so that I can tell you why this is wrong. Just because you get infinity minus infinity doesn't mean that the difference is going to 0. Here's why. Here's why. See, f of x might go to infinity faster than the other one. They are both going to infinity, but one of them might be going to infinity faster than the other one, so that the difference will not be going to 0. Okay, so let me again explain why it's not going to be 0. Think about this. What's the limit as x going to infinity of x minus x? Notice that what I have is infinity minus infinity, right? That's the limit form. Each term goes to infinity. However, this is silly, right? X minus x is what? 0. So the limit is 0. And now think about what's the limit as x going to infinity of 2x minus x. Once again, you have infinity minus infinity. However, this time the limit is what? No? The 2x minus x is x, so the limit is what? Infinity. Okay? What's going on? Well, 2x is going to infinity faster than x, right? So the limit could be in fact infinity as well. Am I making sense? Okay. So that's why just because you get infinity minus infinity doesn't mean that the limit is 0, okay? So let's do another example. The limit is x going to infinity, x squared plus 1, root of that minus x. Now, what's the limit of the first summand? What's the limit of root of x squared plus 1? Infinity, right? And what's the limit of x? Infinity, right? I have infinity minus infinity. However, what should be the limit of the difference? What should be the limit of the difference? Let me give you some intuition. If you didn't have the 1, right? If you didn't have the 1, it's 0, okay? However, how do I determine this limit? Well, I have really no clue what to do. However, I see root, and if I have nothing else that I can do, I will rationalize, okay? If you see roots, that's why I gave you those exercises on rationalizing. If you see roots, if you have no other clue what to do, rationalize and see what happens, okay? So, okay, so this is what we're going to do. We're going to rationalize. So this is limit x going to infinity, x squared plus 1. Even though I don't have a ratio, right? In the denominator I have what? Oops, sorry, this is x. In the denominator I have 1, right? I'm going to multiply by what? Plus x, right? Root of x squared plus 1 plus x. Everybody's okay with that? You guys are okay with that? Now, what am I going to get in the numerator? Anyone knows? What am I get on? What are we going to get on the numerator? We are going to get the square of x squared plus 1 root of that. We're going to get the square of this minus the square of x divided by x squared plus 1 root of that plus x. Everybody's okay? What am I getting on the numerator then? I am getting x squared plus 1 minus x squared over x squared plus 1 root of that plus x. And basically then I have the limit as x going to infinity 1 over x squared plus 1 plus x. Now what is happening? Now the numerator has limit 1. The denominator has limit what? Infinity. So the limit of the ratio is 0. Is everybody okay with what I said? Say it again? Oh yeah. So we needed to find the limit of this difference, right? So what we are doing is we are rationalizing this guy. In order to rationalize, I'll be multiplying and dividing by the conjugate. So the conjugate of this guy is the root of x squared plus 1 plus x. So I divide by root of x squared plus 1 plus x. Now I multiply the denominators, multiply the numerators. So if you multiply the numerators, you're going to end up with the square of this guy minus the square of this guy. If you want, you can multiply them by using FOIL and see what happens. You're going to get the same answer. So if I multiply out, that's what I get. And then the square of this guy is x squared plus 1. The square is here. X squared and x squared cancels out. And if I cancel out the x squareds, I end up with 1 divided by something which is root of x squared plus 1 plus x. And then as x goes to infinity, the denominator goes to infinity, the numerator goes to 1, so the ratio will go to 0. Okay? Again, in the homework, if you see root functions in the limit, if you cannot figure out anything else, rationalize. Okay? Is everybody doing okay? All right. Okay, so let me do another example. What's the limit as x going to infinity of sine x? Anybody? What's the limit of sine x as x goes to infinity? It's not infinity. It's not 0. It's not minus infinity. What? It's not 1. Yeah, it doesn't exist, right? Well, think about the sine function is doing what? It's going to 0, 1, negative 1, 0, 1, negative 1. It keeps doing that, right? So as x gets bigger and bigger, it keeps doing that. It doesn't approach a number, right? It doesn't approach a number. So it doesn't exist, okay? Another example, the limit as x going to infinity of x squared plus x divided by 3 minus x. Now, when I'm going to do this problem, I am going to do it a little bit differently. So how did we do this problem before? This type of problems. We factor out the leading term, right? The highest power of x. However, what I'm going to do now is sort of say, well, since we are interested what happens when x is big, when x is big, a polynomial, let me say it this way. If we want to know what happens to a polynomial when x is big, the leading term matters. The leading term is the dominating term. So here, this guy is the dominating term. Here, this guy is the dominating term. So when x is big, the other terms don't matter. Okay? And so imagine that you only have x squared divided by negative x. Then what's the limit? Okay, what's the limit? Well, I'm saying what's the limit? What's the limit as x goes to infinity of x squared divided by negative x? That's equal to the limit as x going to infinity of negative x, right? So this would be negative infinity. Am I making sense? So this is like a shortcut. Instead of factoring out, if you factor out x squared, if you factor out x here, and do this problem that way, you will still get the answer to be negative infinity. Am I making sense? So when you have a rational function and you're looking at as x goes to infinity, then only the leading terms matter. Okay. Okay. what I want to tell you now, give you the definitions of asymptotes, okay? So what is a horizontal asymptote? Horizontal asymptote for a function f. In order to figure out the horizontal asymptotes of a function f, what you need to do is you need to compute the limit as x going to infinity of f of x. Let's say the limit of f of x as x goes to infinity is L. And let's say the limit as x goes to negative infinity of f of x is some other number m. Okay? Then the horizontal asymptotes of f, the horizontal asymptotes of f are the horizontal line at L and the horizontal line at M. Am I making sense? If the limit of f at infinity is L, then I have a horizontal asymptote at height L. If I have the limit of f to be M at negative infinity, then I say that I also have a horizontal asymptote at height M. Let me explain what we mean by this by a couple of examples here. Let me know if you're done writing it down. Are you done writing it down? Okay. So let's look at an example. Let's think about the function f of x, which is x plus 1 divided by x. And we want to figure out the horizontal asymptotes of this function. So the question is find the horizontal asymptotes for f. Okay. So how do we find the horizontal asymptotes? Well, we just find the limit as x goes to infinity of x plus 1 over x. What is that limit? One. So that tells you you have a horizontal asymptote y equals to 1. Okay? What's the graph of the equation y equals to 1? That's the horizontal line at height 1. You also have to look at what's the limit as x goes to negative infinity of x plus 1 over x. Well, in that case, that's equal to what again? 1 as well. So you only get one horizontal asymptote. If the limit of if the second limit was a different number, then you would be getting two different horizontal asymptotes. Okay, so we have only one horizontal asymptote in this case. So graphically, what does it mean to have a horizontal asymptote? What it means is that you have the horizontal line at 1, right? And the graph of the function is getting closer and closer to that line. The graph of the function is getting closer and closer to that line. For example, the easy example is, notice that if I look at the limit as x going to infinity of the function 1 over x squared, then I get 0, right? So what's the horizontal asymptote in this case? Y equals to 0, that's the horizontal asymptote. And y equals to 0 is the x-axis. So let's look at the graph of x, 1 over x squared. Yeah, this was the graph of this was the graph of 1 over x squared. So what happens is that I have a horizontal asymptote at the x-axis. It means that the graph of the function is getting closer and closer to that line. Okay? So generally speaking, go up right here. Right there. So generally speaking, how does the graph of a function look like when it has a horizontal asymptote? Well, let me give you a graph here. Let's say this is my x-axis, this is my y-axis. Let's say I have a horizontal asymptote at this height. So let's say I have a function f of x, and the function f of x has an horizontal asymptote y equals to L. And let's say the limit as x going to infinity of f of x is equal to L. So what it means is that as x gets bigger and bigger, the graph of the function is getting closer and closer to this line. Okay? But it might get closer and closer to this line in many different ways, right? It can get closer and closer to this line this way, or maybe the function is decreasing and getting closer and closer to this line. Okay? What's another possibility? Another possibility is that the function is like this, and the gap between the graph and this line is going to 0. Okay? Sometimes students think that if you have a horizontal asymptote, the graph doesn't cross that horizontal asymptote. That's a wrong idea. You can say that for vertical asymptotes, but for a horizontal asymptote, it means that the gap between the graph and the horizontal asymptote is decreasing to 0. Okay, so it might intersect the horizontal asymptote. So one of the three might happen when you have a horizontal asymptote. Is everybody clear? Okay. We are going to use this horizontal asymptotes. By the way, what's the meaning of a vertical asymptote? If you have a vertical asymptote, it means that the function is going to infinity or negative infinity near that, right? Okay. All right, I think I'm going to end here. This is the end of section 3.4, and so I am going to give you the homework. And so this is it for your exam on Friday, okay? Okay, section 3.4, please look at the problems 9 to 29 odd. 9 to 29 odd. And then 33, 35, 33, 35, and 48, sorry, not 48, 49 and 51, 49 and 51. Actually, sorry, never mind. Can you cross out that the last two? I said 49 and 51. We are going to talk about those problems in another section anyway, so let's just not do that. Okay, so this is it that I said. So your exam on Friday would be what? We finished, yeah. I gave you the 1.5 yesterday?
No.
Oh, I didn't.
Just 1.4. Right.
Okay,
One
okay.
question, yeah, number 3.
Let me give you 1.5 then. I thought I gave you 1.5 together with 1.
No, you just gave us number 3, 1.4.
Okay, 1.5. Okay, 1.5, I want you to look at problem 1357. 1357. 11, 15. And 29, 31, 33, 35, 37. Okay, let me say it again. 1357, 1357, 11, 15, 29, 31, 33, 35, 37. Wait, I also have 1.6. You're done with that? Did you write that down? 37 was the last. Okay. Section 1.6. Section 1.6, problem 1, 3579. 3579. 11 up to 31 odd. 11 up to 31 odd.
1 through 31 odd.
Is that again?
1 through 31 odd.
Yes, pretty much 1 to 31 odd, yes. And problem 37 and 41. 37 and 41. Okay. So tomorrow, I know there's a lot of homework problems, but tomorrow you should try to keep me busy, okay?
This is a good review.
Well, you can make it a review if you keep me busy with asking me questions, okay? So if you don't ask me questions, then I will start something new. So let's see how long you can keep me busy tomorrow, okay?
Oh, just as we get out, of course.